This is McGraw-Hill Chapter 7, Section 2, Quadratic Formula. Make sure that you understand that the quadratic formula is x equals negative b plus or minus square root of b squared minus 4ac over 2a. And that comes from the fact that you're dealing with a trinomial where a is the coefficient in front of x squared, b is the coefficient in front of x, and c is the constant. Also realize we're going to do problems where we define the discriminant. The discriminant is b squared minus 4ac, which is located underneath the square root sign. What happens is if b squared minus 4ac equals 0, then that eliminates this part of the equation, so all we have is negative b over 2a, which means we have one real solution. If b squared minus 4ac is greater than 0, then this becomes the square root of a positive number, which means we have plus or minus, which means we have two real solutions. If b squared minus 4ac is less than 0, meaning negative, then this becomes imaginary, which means we have a real added and subtracted to imaginary, which makes it complex, two complex solutions. So here's the first one. Example 1 says, solve 2x squared minus 3x equals 5. So we subtract the 5 over. A is 2, b is negative 3, 5 is negative c. First of all, if we could factor, we would want to factor. This is non-factorable. If we could solve it algebraically, we'd want to solve it algebraically. The quadratic formula is the last resort. So we plug 2 in for A, we plug negative 3 in for B, we plug negative 5 in for C. Do the math, we get x equals 3 plus or minus square root of 49 over 4, which gives us 3 plus 7 over 4, which is 5 halves, 3 minus 7 over 4, which is negative 1. So our two solutions for x are 5 halves, negative 1. When we come here, okay, this is example 2, page 593, we have negative x times x minus 6 equals 11. So what we do is distribute the negative x, so we get negative 1x squared plus 6x, subtract the 11 over minus 11. So a is negative 1, b is 6, c is negative 11. Plugging the numbers into the quadratic formula and doing the math, we end up with negative 6 plus or minus square root of negative 8 over negative 2, which then gives us negative 8. We bring the I out, and then 8 becomes 4 times 2, which is square root of 4, so it becomes 2i square root of 2. When we divide the negative 2 in there, we get a positive 3, and then we get a minus, plus or minus, I square root of 2. So what we did here was reduce the fraction. Put the negative 2 underneath the negative 6, and the negative 2 underneath the 2i square root of 2. Here's where we find the discriminant. Okay, I didn't do example D in example 5 because it dealt with fractions, and I'm not going to give you one with fractions. So 2x squared minus 5x plus 9. So here's our b, here's our a, here's our c. Plug it into the b squared minus 4ac, we get negative 47. So there's two complex solutions. When we get a negative value for the b squared minus 4ac, it's two complex solutions. Here's letter b, 3x squared plus x minus 2. Here's our a, here's our 1 is our b, negative 2 is our c. Plug it in, we get 25, which is a positive. If it's greater than 0, it's two real solutions. Here's negative 4x plus 6 plus 1, which is letter c. Plug negative 4 in for a, 6 for b, 1 for c. We get 52, which is two real solutions. Example 6 tells us that given f of x equals 1x squared minus 3x plus 1, where 1 is a, negative 3 is b, and 1 is c, find the discriminant and x-intercepts. All right, so plugging it into b squared minus 4ac, we get 5. So we know we have two real solutions. Now, as far as x-intercepts go, if my b squared, for my discriminant, b squared minus 4ac is positive, we have two x-intercepts. If my b squared minus 4ac is negative, we have no So in this case, because this is positive, we have two x-intercepts. It says find the y-intercept. Well, if we want to find the y-intercept, we've got to plug 0 in for x. So if f of 0, then we got to plug 0 in here, which we get 0 squared. Got to plug 0 in here, we get negative 3 times 0 plus 1. So we find out that f of 0 equals 1. So our y-intercept is 0, comma 1. Remember, way back in chapter 2, I think it was. If I want to find a y-intercept, I plug 0 in for x. If I want to find an x-intercept, with algebra, I plug 0 in for y. But in this case, when we're working with quadratics, we got this rule here where we can look at the discriminant and determine how many x-intercepts we're going to have. It's not going to tell us the x-intercepts, but it's going to tell us how many we have.